All right. This is asynchronous week 16. I know it seems like how can this possibly still be going on week 16? The semester is long. That's how. But as I explained to you in class on Wednesday, I don't have any new material for you. I don't want to throw anything else asynchronously at you for this exam. The only thing I want to do is finish up the last area example that I had to show you in class that I just didn't have time to do, which didn't surprise me, just because there's a lot to do with area. Surprised we got done with as much as we did. But that's good because now we can just focus on this last example I have for you. We're going to be using the same function in all three parts of this example, but, or I should say the same polar equation, but we're just going to be setting it up slightly differently depending on the region that we're looking at for the area. So this is just a continuation of 9.6. Here's the example I was going to do with you. I believe it is example 5. I believe it is example 5. I don't want to make this super confusing. The last one we did, yes, was example 4. Okay. So we are going to consider the circle r equals 1 and the cardioid r equals 1 plus the cosine of theta. The first thing we're going to do is we're going to find the area of the region outside the circle and inside the cardioid. Okay, in order to do this, we're going to need to have a nice graph so that we can really see what's happening with our area. Remember, just like with chapter 6, when you're finding area for functions, it's not required to graph this, but it will surely help you to see what's happening in the figure. Oh boy. Try to keep this low here so I don't get that glare. Okay, we are looking at r equals 1 and r equals 1 plus the cosine of theta. And we're going to graph these together. Right now, I am set from 0 to 2 pi. Remember that r equals 1 is just the circle centered at the origin with a radius of 1. So we're going to end up needing to zoom in a little bit more closely here. But go ahead and graph this. There's your circle. And there's the cardioid. So I'm going to zoom to, enter. There's your circle. There's your cardioid. Okay. I'm going to do a little tiny representation of this here so that we can try to outline the region that we're looking at area-wise. Okay, so let's say that this is the radius of 1. There's your circle. We'll say this is r equals 1. And then for the cardioid, it's not exactly clear, but it appears that your cardioid intersects the circle here. We can determine that first before we graph it, if you'd like, and maybe we should do that. Find that intersection point between the circle and the cardioid. And we'll do that, remember, by setting these equations equal to each other. So I'm going to have 1 equals 1 plus the cosine of theta. And then when I subtract 1 from both sides, I end up with cosine theta equals 0. And we know that if that's the case, then theta must either be pi over 2 or 3 pi over 2. And that matches up with what we're seeing in this picture in our graphing calculators at theta equals pi over 2 and theta equals 3 pi over 2, you're seeing that you have these intersection points. So those are going to be right here on your graph. And then your cardioid kind of does something like this. And it goes through 2. So it's going to go up a little bit higher than your circle. Going to go through 2-ish. No, 2 exactly. Should have made it a little bit lower, but you get the idea at this point. Okay, so the picture in and of itself, the intersection points, those things are a little bit more straightforward. What I really want you to focus on here is making sure that A, you have the correct region, and B, that you know how to find the area of that region. And we're going to use symmetry again, just like we did in our class examples. So we're looking for the area of the region outside the circle and inside the cardioid. So it's got to be inside the cardioid, so somewhere in here, but it cannot be in the circle. So if it can't be in the circle and it has to be inside the cardioid, the only place for our area to exist is in this region. Okay, so here we are outside of the circle. So notice your circle here is not shaded anywhere, and inside the cardioid. So there we are. So this is what we're looking at right now. If I want to find the area of the shaded region, what I'm going to focus on doing, and you don't have to use symmetry, but I think that's the easiest way of doing this, is I'm first going to find the area of the top half of the region, and then I'll just multiply it by 2 so that we can also get the area of the bottom using symmetry. Now, in order to do that, we need to figure out exactly where we're going to be getting our limits of integration. So notice that, oh, I'm so paranoid, this thing's not recording. Okay, we're recording. Notice that as you move your way up through your angles, so here we have theta equals 0, right, sitting on this line. And then theta keeps increasing, 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 goes up and up and up and up. And then eventually theta gets to this value, pi over 2. And that was where we had this intersection point where your region ends. Where your region ends at this intersection point is where you're going to have your upper limit of integration. And remember, you can always test these values. Remember also that you can always graph this using whatever window you'd like. And we did that in class too. So you can even look at this using theta from 0 to pi over 2 and verify that you just get this region. I mean, of course you would because you're in quadrant 1, but pi over 2, yikes. I think this is going to zoom me back out, but that's okay. We'll graph it. No, it stayed in. And there you go. So if you're just going from 0 to pi over 2, you just get what's happening in quadrant 1, and you're just getting this region of the top half. Of course, you could take this from negative pi over 2 to pi over 2, and you'd get the whole thing. You could always integrate from negative pi over 2 to pi over 2. You could do that, and then you would still get the area of the region. In that case, we wouldn't multiply it by 2 because we wouldn't need to, because we wouldn't be using symmetry. All right, so that's always an option that's available to you. So I'm going to set this up by taking twice the area. So that's where the symmetry comes in of the top region. If you are not using symmetry, you're going to go from negative pi over 2 to pi over 2. I'm going from 0 to pi over 2. Just make sure that you note that if you're not using symmetry, you cannot go from 3 pi over 2 to pi over 2. You're going to end up getting a negative area, and it's not going to be the area that you want because essentially you'd be going backwards. You have to go from least to greatest when you're looking at your limits of integration. So you'd have to go from negative pi over 2 to pi over 2, not 3 pi over 2 to pi over 2, because you'd be going that way. You get a completely different value. Okay, so what we're going to do here is we're going to focus on taking, I mean, if we're thinking about sort of jutting this arrow out through the region, what we're going to take is the area of the cardioid minus the area inside the circle. So it's kind of like if you're just isolating this in quadrant 1, it's as though you were taking this whole area of the cardioid, but now you're just taking off the part that's not shaded, which is the circle. So remember that our equation is going to be 1/2 times the integral of r squared d theta. So when I end up subtracting that area off, I'm just going to take that outer region squared minus the inner region squared. So the outer region, I didn't label that one, but it's 1 plus the cosine of theta minus the inner region, which is just 1 squared, technically, d theta. So this is the outside minus the inside. Some of you will think about this in terms of subtraction, where you're just subtracting off the area that you're not using, and others will really think about this more as like taking one curve away from the other. Okay. Now that you have your integral set up, at this point, this looks very much like a bunch of the integrals we've already done. So I'm going to go through this one a little bit faster as far as evaluating the integral. So 2 times 1/2 just gives us 1. So I can rewrite this now as the integral from 0 to pi over 2 of 1 plus 2 cosine theta plus cosine squared of theta minus 1 d theta. And then remember that the cosine squared of u is 1/2 times 1 plus the cosine of 2u. So we're going to use this identity to rewrite cosine squared. And notice also that these ones are additive inverses, so those are going to be gone. So that leaves you with 2 cosine theta plus, and then 1/2 plus 1/2 cosine 2 theta d theta. So I just distributed this 1/2 into the parentheses here for your identity. And now we will go ahead and integrate. Whatever you do, don't combine these. Remember that cosine theta and cosine 2 theta are not like terms. You can't add them together. All right, so let's see. We have 2 sine theta plus 1/2 theta, and then plus. Remember that when you are integrating, you're going to divide by k. So 1/4 sine 2 theta. And you're going to take that from 0 to pi over 2. So we have 2 sine pi over 2 plus 1/2 times pi over 2 plus 1/4 sine 2 pi over 2 minus 2 sine 0 minus 1/2 times 0 minus 1/4 times the sine of twice 0. So 0, 0, 0. And also this one's going to give you 0 because 2 times pi over 2 is pi, and the sine of pi we also know is 0. So the only values we're using here are going to be these two. The sine of pi over 2 is 1. So you're going to have 2 times 1 plus pi over 4. And that just leaves you with 2 plus pi over 4. Okay. Okay, so that is an example of finding the area of this shaded region. Remember, we use symmetry so that we could get the area of the whole thing. When we multiplied it by 2, that gave us both parts of this shaded region. Now, let's see, which one will we do? let's switch the region up slightly. It's going to be the same type of idea. The reason I want to do the same example, just setting it up differently, is because the setup is what I think is going to cause you problems, if anything, just like with the applications that we worked on in chapter 6. There's like a delay on my screen. My computer's running slow. Big shock. I really haven't restarted it in probably weeks. That would probably solve a lot of my problems if I would just restart my computer. I'm going to do it tonight. I swear I'm going to restart this computer. B. Find the area of the region. Inside the circle. And outside the cardioid. Or if it's delaying for you guys too. I think it is. Yikes. You can see it a little bit better. Okay, so I'm gonna redraw our picture here. Same idea. We still have this circle with a radius of 1. And we still have this cardioid intersecting your circle at pi over 2 and negative pi over 2. Looks kind of like this. Okay, and we're looking for the region inside the circle, outside the cardioid. So if it can't be in the cardioid, it cannot be in any of these parts right here, but it's got to be inside the circle. And what we're doing here is looking at this piece. So inside the circle, outside the cardioid. Okay. Wonderful. So last time we focused on finding the area here. This time we can again use symmetry, but we're going to be looking at something slightly different, but the same type of idea. This time, instead of looking at our outside function as being 1 plus cosine theta, our outside is going to be r equals 1. We're also going to need to think about our limits of integration. So we said that these graphs intersected at pi over 2. So in this case, instead of going from 0 to pi over 2 like we did last time, in this case, we're going to go from pi over 2 down to pi, because that's the region that's covered here. We're just sticking in quadrant 2 at this point. So if they intersect at pi over 2, that means that we can start at pi over 2, and then we're going to take this down. If you liked my pencil maneuver, you can think about it that way. So you're starting here at pi over 2. Your theta goes down, 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 covers this whole region until you get to pi. You could, of course, take this from pi over 2 to 3 pi over 2 this time. If you wanted to do the whole thing instead of using symmetry. I tend to just like using pi because I feel like a lot of stuff is going to end up canceling out for me differently if I use pi instead of 3 pi over 2. In general, I find it's easier to find trig function values at pi than 3 pi over 2 for whatever reason, but that's up to you. So we're going to set this up as twice because I'm going to use symmetry. And then our area is going to be 1/2 times the integral from pi over 2 to pi, just looking at that second quadrant. And then the same idea as last time. What we're going to be doing is it's like we're taking the area of just what's happening in the circle, but we then have to take off the area of the part that's not shaded. So we would have taken the area of this whole second quadrant, but we can't because we need to get rid of these humps here that aren't supposed to be part of that region. So we're going to go, again, outside minus inside. So if you're thinking about taking that region up through here, you would be just taking r equals 1 as your first function, and then taking off the area of your cardioid. So 1 plus cosine theta squared d theta. So just kind of the same idea in reverse. Just notice that even though this looks very similar to what we did last time because we switched the order of subtraction, you also are dealing with different limits of integration than you were last time. So let's go ahead and, again, we've done a bunch of these now, but we'll go ahead and evaluate this. So we have 1 minus, and then be careful to make sure you distribute that negative into your parentheses, 1 plus 2 cosine theta plus cosine squared theta d theta. And then the 1 minus 1 will, of course, give you 0. And then you'll have negative 2 cosine theta minus cosine squared theta d theta. And then we're going to switch this cosine squared using a power reducing formula. So this will still be negative 2 cosine theta, but this time you'll have this minus sign, which is still there, 1/2 times 1 plus the cosine of 2 theta d theta. I'm going to simplify that in the next line. Okay, so we have negative 2 cosine theta minus 1/2 minus 1/2 cosine 2 theta d theta. If all these negatives are bothering you, you are more than welcome to factor it out. The only reason I'm not doing that is because I don't want to end up forgetting about it at the end. So I'm just going to hang on to them. I know when we integrate it, sometimes we're kind of like, I'd rather not look at the negative. I'm just going to keep mine there, but that's up to you. That's just an integration thing. So the integral of cosine theta is sine theta. And, you know, we just integrated this basically. And the last example we did in part A. So we have that now, and we'll go ahead and evaluate that from pi over 2 to pi. And you'll have negative 2 sine pi minus 1/2 pi minus 1/4 sine 2 pi. And then now when you subtract off the lower limit of integration, you can just switch all these to pluses. So you'll have plus 2 sine pi over 2 plus 1/2 times pi over 2 plus 1/4 times the sine of twice pi over 2. So the sine of pi is 0. The sine of 2 pi is also 0. The sine of pi over 2 is 1. And this will be the sine of pi, which will give you 0. So we have negative 1/2 pi plus 2, and then plus pi over 4. So negative pi over 2 plus pi over 4 leaves us with a negative pi over 4. So really similar to what our answer looked like for A. And if you're doing a comparison, just to sort of look at this numbers wise to see if your answer makes sense. Well, in the last example, we had a greater area. We had 2 plus pi over 4. And in part B, we have 2 minus pi over 4. And if you notice, just from looking at the regions here, it would make sense that for B, when we're looking for the area of this region, it would be less. than it would be for this region A, which is clearly a larger region. So if you're taking 2 and adding pi over 4 to it for A, you're getting a larger number than if you took for part B 2 and subtracted pi over 4 from it. So that's a smaller value, which is what you'd be expecting here, that for B, the area of your region would be less than it would be for A. Okay, so I'm going to do one more setup with this, and then we'll call it a day, because I feel like I gave you enough homework to work on. You have enough to keep you busy till Wednesday, getting ready for that last test, and then sort of charging into the final. It'll be awesome. Okay. So for C, we are going to find the area of the region inside the circle and inside the cardioid. So this is not like one of those algebra questions where it's like an and or an or. This is an and, I guess, if you wanted to think about it as an algebra question. The and is like an intersection, and the or would have been like an either or kind of thing, or like it encompasses everything. What we're looking for here is the intersection of these two regions. So we're looking for the region inside the circle and inside the cardioid. So it has to be the region that's common to both of those figures. So I'm going to graph this one final time. I have my intersection points here at pi over 2 and negative pi over 2. I know that my cardioid is going to go up kind of like that. Doesn't have to look perfect. Thank goodness. It just has to be a general gist. Okay. Something like that. All right, so if I'm looking for the region inside the circle and inside the cardioid, I have to be inside both of them. So if I'm over here, I'm outside of the cardioid. If I'm over here, I'm outside of the circle. So in order to be inside both of them, I need to be in here. It almost looks like just a smaller cardioid, but not quite. So here's r equals 1, and this was r equals 1 plus the cosine of theta. Now we already know they intersect at pi over 2 and 3 pi over 2. So we have that. So here's my plan. I'm going to get the area of the region in quadrant 1, and then I'm going to add that to the area of the region in quadrant 2, and I'm going to multiply both of those by 2. Find the area of the semicircle and add it to the area of the two humps. Okay, so here's your semicircle, this region that's just to the right of the y-axis. So I'm going to find that area, and I'm going to add it to the area of these humps. Now, some of you might be wondering, like, okay, this is a circle. I know how to find the area of a circle. Why can't I just do 1/2 times pi r squared and just get half the area of this circle, r equals 1? That's fine. If it's just a circle and you just want to use geometry to find that area, that's okay. So we're talking about a radius of 1. The semicircle is just going to be half of your circle. So we know that if it was the whole circle, r equals 1, the radius would be pi r squared, but it's only half of that. So it's 1/2 pi r squared. If r is 1, that's just 1/2 pi. I'm going to do this though using calc. So use geometry if you'd like on your test. I'm okay with that. If it's a circle, no big deal. But I'm going to use calc. So what I'm going to do is I'm going to take twice for symmetry, because I'm just looking right now at quadrant 1, the area from 0 to pi over 2. And remember, the 1/2 is just part of your formula. So I'm going from 0 to pi over 2 of 1 squared d theta. This is what I was saying you could use geometry for. And I'm going to add that to twice. I could have technically just combined all this into one integral. Maybe I will in the next step. Well, actually, I can't. Never mind. Never mind. I don't have the same limits of integration. I can't do that. I'm going to add this to twice, and then we have a half. Now we're going to go from pi over 2 to pi. So this covers this region in quadrant 2. Remember that you have this angle pi over 2, and you're just covering values on this hump as theta works its way down to pi. I know sometimes that can be hard to see with these because it doesn't seem like that's happening. But remember, if you have this radius, it does, as theta continues to increase, it does get smaller down to 0 as you head towards pi. So we're going to go from pi over 2 to pi, and we'll take the area of this region, 1 plus cosine theta squared d theta. And then we'll just take these two areas and add them up. I'm going to look at this one on the left first, and then I'll do this other one on the right, because this one is obviously going to be fewer steps. So I don't want to try to make it look like they're the same number of steps, because they're not. So this is theta from 0 to pi over 2, which is just going to be pi over 2. Now here, you're going to have pi over 2 to pi of 1 plus 2 cosine theta plus cosine squared theta d theta. And then we have 1 plus 2 cosine theta plus 1/2 plus 1/2 cosine 2 theta using that identity. And then go ahead and, I mean, you could add those two together, I guess. I'm going to, because I hate having these constants just sitting there like that. I like to combine them when I can. So 1 plus 1/2 gives us 1.5 or 3/2. Okay, now we'll integrate. So this will be 3/2 theta plus 2 sine theta plus 1/4 sine 2 theta from pi over 2 to pi. So I'm still carrying this pi over 2 around from the first integral for the circle. And then we have 3/2 pi plus 2 sine pi plus 1/4 sine 2 pi minus 3/2 times pi over 2 minus 2 sine pi over 2 minus 1/4 sine 2 pi over 2. Check all your signs, SIG and S, just to make sure they're correct. So these were all positive, so we're positive here, and then these should all be negative using the FTC. Go ahead and start combining. If you're noticing here that you have 1/2 plus 3/2 and then minus 3/4, you can go ahead and combine those together. So 1/2 plus 3/2 is 4/2, which is 2. So you're going to have 2 pi and then minus 3 pi over 4. You can do that in another step if you'd like. That's going to give you 0, 0, and 0. And then this guy will just give you minus 2. The sine of pi over 2 is 1. So 2 pi minus 3 pi over 4, get a common denominator. You have 8 pi minus 3 pi is 5 pi over 4 minus 2. And that is how you would do this examples, just switching those regions around. So when we were in class, I gave you an example where your intersection points were, I think you had 2 circles in class. Yes, you did. The last example we did together last Wednesday, you had 2 circles and then they intersected at like pi over 3 and 5 pi over 3. So this one is a little bit different. And this time we used a cardioid and a circle instead of 2 circles. But hopefully you're able to kind of compare this to what we did in class. And the goal is just to sort of see a bunch of different examples, just sort of, and be able to synthesize all of your information so that you end up coming up with a really good plan for how you're going to approach these problems when you see them and how you're going to figure out the area of your regions. Okay. Like I said, I don't want to inundate you with examples. These are the only types of examples I have. You're not going to see any other types. At this point, it's just you being able to piece this together, work on some of these for your homework, just so that you get a really good sense for what to do. Now, remember, some of these on your homework, I don't know, maybe you've already started it, but some of these are going to be a little bit more basic, where it starts out like what we did in example A, where it's just like, find the area of the cardioid. But then there will be some later on in the assignment where you're going to be looking at the area between 2 parts of 2 different regions. So it kind of just depends. And then there was at least one rose curve one on your homework where you were asked to find the area of like a petal, like I did in example 2. Just looking at what I did in class the other day to try to remember which one was which. And then we did one with an inner loop. And then we had these intersection ones. So that's pretty much what we're going to be doing for area. That pretty much covers everything. And there's nothing else to do. When a class ends, it just happens so suddenly, where it's just like, wait, this is the last topic. There's nothing else to cover. But that just happened. This is the last topic. There's nothing else to cover. So I put up some homework for you already. It's already up there. So hopefully this will just be a good aid in continuing to work towards that. If you have questions, feel free to email me or come to the office hour on Monday. It's definitely easier for me to help you in the office hour when we're talking through it in real time versus me like sifting through any work that you send or any sort of abstract questions. But of course, if you wanted to send me work, that's fine. If you had a question about a homework problem, usually if it's a quick question, email is perfect, because then you can get it out of the way. You don't have to wait till Monday's office hour. So I would highly suggest coming to the office hour on Monday if you do have questions. Now, I was looking at my stuff and I was trying to see if I had some sort of review. And it looks like I do. Final review. I'm going to look through it just because there might be some things that maybe not necessarily that we didn't cover, but maybe we didn't go into as much depth, or maybe there was something I wanted to add to it. But I am going to post this for you at some point this weekend. I know I don't know when you're going to be watching this video. It's going to be posted soon. Today is currently, I'm in like the wee hours of the morning on December 3rd. So I'm going to post this coming weekend. So that would be like December. Oh, technically this is technically the weekend. So like December 4th, 5th. I'm going to post this final exam review. Now I'm posting it with the full knowledge that you're probably not going to get to this until at least Wednesday night after your exam. But I do want you to try to get a good head start on it. I do have, I believe, a key for this somewhere. I don't see it in here, but I'm sure it exists. And I will post the key but this is basically going to be a pretty comprehensive review of what we've done in this class, kind of taking you over everything, starting from chapter 6 and ending in chapter 9. So I'm like leafing through it right now, and I'm seeing a cylindrical water tank. How much work is done filling the tank half full of water through a hole in the bottom? Oh, you guys remember that? I'm even seeing like convert from polar to rectangular coordinates. But I am, as I'm looking through this, I don't even know when the last time I used this was, but it has a question about finding concavity for parametric equations, which we didn't do. So something like that, I need to make sure I take out of here, just because I don't want you to be confused and be like, wait, are we responsible for this? Because I never asked you to talk about concavity in this whole class. So I am going to have to just go through here and tweak this a little bit. But I'm definitely going to try to post it at some point this weekend by like the end of Sunday, just so that you have it. And then if I don't have a key for it, I'm going to have to make one, which is not the end of the world. I'm sure there was a key somewhere. It might be handwritten and in a notebook somewhere. A bunch of series on here. I think I did add some things to it last year, now that I'm looking at it. Okay, it's 11 pages, so it's going to definitely be longer than your final. So if you were wondering, like, well, how long is the final going to be? Your final is going to be about as long as a regular chapter test. I can't have it be 11 pages because you have to still be able to take it during our normal class time. So, I mean, sure, I would be able to cover everything comprehensively in 11 pages, but you would be sitting there all night. And it would take me forever to grade it. So I really kind of have to pick and choose what type of problem I'm going to put on your final exam. Just, to make sure that I feel like we're covering all of our bases and hitting all the important things. So I will be posting the final exam review. I'll put a key up shortly after I post the review. I'll have to see if I have one or if I have to make a whole key. And if you have questions on that, that's what we're going to be doing during our review session, which is going to be in place of asynchronous week 17. So this is week 16. So technically, we're supposed to have an asynchronous class week 17, and that's going to be the review class. So what I'm very likely going to be doing is just setting up a time, probably. If you prefer it over the weekend, we could do it over the weekend. It would be the weekend of the 10th or something. So I'm looking at my calendar right now. It's opening. Maybe December 11th, if you wanted to do a Saturday. Oh, that day's a little bit crazy for us. It might have to be the 12th. That day's actually crazy for me too. We're going to come up with a time. If I have to do it Friday night, the 10th, that is not that I know of a crazy day. So maybe we'll do it the 10th on a Friday, if that works. I might send up out a survey for times that would work for people. For the review session, it's not during our regular class period. If you can't make it, that's fine. I know that it sucks if you can't make it because I would like for everyone to be there, but obviously I know that everybody's got different schedules. But I will be recording it. So I'm not even going to be planning out anything that I'm going to be doing fancy with the review. It's going to be you asking me questions, me answering the questions. And if you don't have any questions, that's fine too. If you want to sit during the session and work on problems and pop in and ask me questions, that's fine. I'm going to be recording the whole thing though. So if you can't make it, it'll be posted. But like I said, we'll probably have it that Friday, the 10th, just because I know I just made my calendar 5 minutes ago. And I know that day is going to be clear for me. If nobody can make it, then there's no point. If I don't know, we'll see. This is a whole different ball game, and we're down to 11 of you right now. So, okay, so that's my plan. I'll email you about the final review session, which will be the weekend before. the final, and then you'll still have that office hour Monday before the final. Also this coming Monday before test 4. I know I just threw a lot of information at you, but there's just a lot that's going to be going on in the next 2 weeks. Email me if you have questions. I'll post this as soon as I go through and tweak it. That's all. Hopefully I'll see you Monday for the office hour if you have questions on any of your 9-4, 9-5, 9-6 homework. Oh, and don't forget that you have homework to do by hand for that graphing stuff. I think it was only 3 or 4 questions, and it was from 9.4. No, I think it was the early part of 9.5. Yes, graphing polar equations, 9.5, not 9.4. I'm pretty sure it's 9.5. But I posted a folder for you to submit your written work on D2L. It's under the assignments tab where you would normally submit your exams. So you can submit your written homework there, and hopefully hopefully it's helpful to at least have the written homework versus doing the graphing on Achieve. Okay, wonderful. You guys have a wonderful weekend or whatever it is when you're watching this. Study hard for your test 4, and have that final exam on your radar so that you're not just like, oh my gosh, it's almost here and I'm not ready for it. I mean, just be thinking about it. Okay, that is all. Wonderful. See you guys soon. Okay. Adios.